My name is James Swistowski. I'm the chair of the AERA SIG on systematic review and meta-analysis. And I'm pleased today to welcome you all to our continuing online seminar in systematic review and meta-analysis methodology. This morning, I'm really pleased to be able to introduce Ryan Williams, who is a famous Australian freestyle scooter and BMX rider, known to his friends and Instagram followers as R. Willie. If you haven't seen his YouTube channel, check that out. Those tricks are sick. Oh no, wait. I got my notes screwed up here. No, so let me try again. This morning, I'm very pleased to introduce Dr. Ryan Williams, who holds a PhD in quantitative research methodology from Loyola University. And he's now a principal researcher at the American Institutes for Research. Ryan is an expert in meta-analytic methodology. I don't know so much about his BMX skills, but he does also have expertise in quasi-experimental design and program evaluation. At AIR, he's served as the principal investigator on a really very ambitious large-scale synthesis of evidence on mathematics interventions for K-12 education, which I think he'll be sharing a bit about today. He's also a co-PI and instructor on the Meta-Analysis Training Institute, which provides intensive training in advanced meta-analysis methods, and I believe is coming up again this summer. Is that right? Yep. Ryan's work is really notable for being ambitious, extremely well planned and executed, and for using analytic methods that push the field forward in terms of the state of the art. It's also, I happen to have seen, his work is also really remarkable in its level of transparency and openness. If you're looking for models for how to actually do the analysis and the research synthesis, go dig through his code. It's excellent. So given that, today I'm very excited to welcome him, and I look forward to learning about how he's thinking about conceptualizing moderator analysis in large-scale research synthesis projects. So I will pass it over to Ryan. I think he'll talk for maybe, 30, 45 minutes. If you have questions during his presentation, you're welcome to drop them in the chat and we'll monitor them. Or if you're also welcome to just wait till the end of his presentation and we'll have some discussion time at the end. So let me pass it over to Ryan.
Thanks, James. Are you all seeing notes page or slide page?
I'm seeing the presenter view.
Okay, let me switch that. How's that?
Great.
Okay. Thanks, James, and thanks, everybody. I'm glad I get to chat about this project with you all today. And all of the accolades that James was sending my way, I certainly can't accept in full. We had a great team to do this project. So Martina Sitkowitz, David Miller, Jim Lindsay, and Kirk Walters were all instrumental in this very ambitious systematic review and meta-analysis. And so, in fact, David was the lead analyst, and he's really the key person responsible for all of the wonderful code and transparency. So thank you, David. Okay, I should also preface this with a note that I am not a machine learning expert, but I'll hopefully describe how we got into this area of inquiry and what we learned from it today. So I'm hoping to kind of give you all a little bit of an insight into the project as a whole, how we ended up navigating issues that we uncovered with our meta-regression model, and how we plugged in some machine learning type algorithms to help us better understand what we might be missing. And then hopefully we can finish up with some of my initial thoughts on strategies and considerations, but hopefully that's also a useful segue into broader discussion. So hopefully we can get through all of that. And if you have questions, put them in the chat. I'll get to them probably after the presentation, unless there's something urgent. James will send up a flare. So here we go. Oops. Oh, I should also say thank you, IES. This was funded by an IES research grant in the STEM program area. And so thank you, IES, for the support. Okay, so what was our goal as kind of an entire project? We set up this broad kind of landscape review and meta-analysis, not to look at any particular intervention's average effect in the K-12 math education space, but we wanted to really start to get into what are some sources of effect heterogeneity that we're seeing across that landscape. And so that was really the priority here. So not necessarily average intervention effects, but really what are those features of the samples, the interventions themselves, the outcomes, the methods, the settings that tell us something about why some effect sizes are larger than others. And that was the goal. All right, so where we started and where we ended up for this portion of the study. So we initially identified around 9,000 abstracts in our search. We ended up full text screening about 2,500 of those, and ultimately we included 191 randomized experiments with a business as usual control group into the meta-analysis. Apologies if you're hearing my dog bark, but something catastrophic like a package delivery is happening upstairs. Okay, what was our framework? So we took the Cronbach's UTOS framework and the Allo and Becker extension of that framework to really kind of structure the main sources of heterogeneity that we were anticipating. So the big buckets were methods. So what are those features of the design or the analysis that might tell us something about variation effects? Units, so these are really the sample characteristics. What do we know about the student compositions in the included studies? What about the treatments? What were some of the different components of those treatments and how were they targeted to different types of learners? Outcomes, so we had a bunch of different types of math outcomes included in the study. And so that seemed like an obvious source of potential heterogeneity. Some of those outcome domains and constructs may be more or less responsive to the types of interventions that were included in the review. And then settings, so anything about the study context, where the learners and the interventions were at during the time of the study. And so we had this MUTOS framework, and we had a plan of how we were going to put all of our moderators together, at least a rough plan. I mean, this whole slide is really kind of like meta-analysis troubles in one slide. Like we all get to this point, we coded a ton of things, and now we want to put it together in some responsible fashion that's hopefully anchored in our original research questions. But inevitably, even at a large review like this, where we had 191 RCTs and about 11 to 1,200 effect sizes, we had to make some hard decisions. And so we needed to come up with a framework, something that was at least modestly principled to make some decisions about how we were going to compile an overall regression model to study variation in these effect sizes. So the approach that we came up with was really, it's kind of like a bit of a tournament. And I was thinking, James, before this would have been a perfect presentation for next month when March Madness kicks off, because everything that I'm talking about is kind of like a tournament. How are things advancing to the final round of analysis? But we'll correct that next year.
Yeah.
And so our kind of bracket structure was, we're going to set up little tournaments with each of the big MUTOS domains. So always controlling for the methods moderators. So among those sample characteristics, adjusting for idiosyncrasies in the research methods, which of those characteristics seem to be most explanatory? And same within treatment, same within outcomes, same within setting. And we used a p-value cutoff, which is, you know, a typical convention with known limitations to help make some of those decisions and advance candidate moderators into a final mixed MUTOS meta-regression model. It's coarse, but we came up with some decision rules ahead of time and we ran it. And of course, we know that by running it this way and not allowing different moderators to kind of mix and adjust for each other across these big MUTOS domains was a natural limitation, something we had in the back of our mind all along. But that was our framework. That was the approach we came up with, and I'll go through what we kind of initially found. So a lot of heterogeneity, really. And this is the only time I'm going to even reference kind of the unadjusted average effect. It wasn't central to our inquiry, but here it is. We're really interested in the tau estimate there. So that tau is a representation of kind of the between effect size and between study heterogeneity. This is a multi-level meta-regression, and so it combines both of those variance components. And so its value is 0.47, which means that we have some prediction intervals that range pretty widely here. And you can see on the left-hand side here, we've kind of broken out kind of the distributions of some of the big intervention types, the curriculum, instructional pedagogical, supplemental time interventions. You can kind of visualize where the average effects are for each of those big groupings, and the colored boxes in the background are 95% prediction intervals. So it's a big space. And so we were expecting this, and we were optimistic that our theoretically grounded MUTOS model would operate as kind of the theory of everything and really tell us why we saw so much variation. So what did we learn? After going through each of those kind of segmented regressions within the U, T, O, and S buckets and advancing the candidates into the final mixed effects meta-regression model, this is what we found. So these are all the variables that made it in. Interestingly, none of the sample characteristics advanced. And so we can talk about that later on, but we did get some, we obviously have some methods moderators in here, some intervention moderators, and really the only contextual variable is publication decade. So there were a few buckets of these moderators that seemed to matter. The values in that first numeric column, mean or B, these are conditional mean effect sizes. So these are the average effect sizes adjusted for the other things in the model. And so we see a little bit of variation in those typical effects across the curriculum, pedagogical, instructional, and supplemental time interventions seem to matter at least somewhat. Intervention delivery mechanisms seem to matter a little bit as well. And there seemed to be a little bit of a relationship between publication decade or time and effect size, slight negative relationship. The big one that we saw, though, was that just stood out in every analysis that we ran was researcher-generated measures versus standardized measures. Those researcher-generated measures were just clearly much more responsive to the interventions that were being studied compared to kind of standardized student achievement measures that would be like state test scores and those types of things. So this is what we found initially, and revisiting the question of how much heterogeneity, how heterogeneous are these effects, and how much can we explain? It turns out we can explain about 10% of that heterogeneity, which was a bit of a sad trombone for us. We thought we had a really good plan in place to kind of really tease apart some of the variation that we had in hand. But it really was a pretty small fraction of the total variation. So this got us thinking, and I remember having a conversation with David Miller, who's chief analyst on this project, back in the office in the before times when we were back in offices. I was like, what are we missing? What could it possibly be? And what alternative approaches could we take to try to get at lost opportunities or missed opportunities in this analysis? What are we leaving on the table? And we both kind of collectively started thinking about, well, maybe we should explore using some of the up and coming machine learning type algorithms that have been adapted to meta-analytic contexts. And at that time, this is a few years ago, these were still pretty new and up and coming approaches. So I didn't have a whole lot of knowledge in them at the time, but David jumped in and really kind of structured this portion of the analysis and ran with it. So we decided to give the job to the machines and see how well they could do. And the two big kind of frameworks that were available at the time, well, it's kind of one framework, right? Classification and regression trees was kind of the big suite of methods that we could draw from. In a simple example, kind of what are classification and regression trees? These are a simple play on regression. So don't let any of the data scientists bully you into thinking that there's some really secret special sauce going on here. It's a version of regression, but the ordering of it and how it's implemented is unique and can be, I think, especially useful in small sample applications, which meta-regression is basically always, even in this big study. So in a simple kind of regression tree, what are we doing? And we're starting with all of our data. So here are all of our studies, all of our effect sizes, and an algorithm that's associated with that regression tree framework is going to try to identify at least one variable that it thinks is related to effect size and useful for splitting the data into two groups that are hopefully more homogeneous with respect to the effect size. So find X1 correlated with effect sizes, let's split the data based on some value, some cut point on that. If it's dichotomous, it might just be the two values that are already there. If it's continuous, it might find a threshold to split the effect sizes or the studies into those two groups. And then it keeps doing that, kind of rolling over the other candidate moderators until it reaches some saturation point. And you end up with this regression tree that results in these classifications or these groupings of data points, studies, effect sizes, so these group memberships have encoded within them all of the complications or all of the complexities of the pathways that got them into that final grouping, which may involve several interactions, several higher order interactions. They may result in groupings that we just wouldn't anticipate. And this was sort of the idea that we wanted. We wanted the data to really just kind of solve itself and tell us what it could see. And then we were then hoping to take a step back and determine, well, is there any theoretical grounding in what the machines are finding in this approach? And that was the idea. So that's kind of the basic classification regression tree framework, as far as I understand. Again, I'm not a machine learning expert, but I think that's a useful overview. We didn't go with simple regression trees. We used a random forest modeling approach, which is what I'm going to talk through in the next few slides. So random forest for meta-analysis has at least these four basic steps or components. So the idea is that we're going to identify from some set of candidate moderators which ones are useful for splitting the data into these homogeneous subgroups, right? So this is the same as like a simple regression tree type framework. And then you're going to recursively do that recursively until some stopping criterion is satisfied, right? So until you get to some point of maximum homogeneity or some minimum number of cases at the end of these regression trees, these terminal nodes, and there you go. Then you finally have this final group of classifications, and off you go. But what makes this a random forest is this third component here, where we basically are going to repeat steps 1 and 2 many times, right? So we're going to leverage bootstrapping methods to generate many possible samples and many possible combinations of moderators that could inform the splits that are happening in these regression trees and forming these final classifications at the end of the day. And then the idea is, over those many possible combinations, those many bootstrap samples, we can kind of pool the predictions from those trees. And that hopefully by using bootstrapping and some other sampling within tree sampling they'll talk about in a moment, we can kind of start to leverage some of the previously unused variation in the data to maybe capture some of those nuanced relationships between our moderators and our outcomes, including those complex and higher order interactions that we just wouldn't have thought about or wouldn't have thought about putting together in a typical meta-regression framework. Okay, so why random forests? Very quickly, they tend to be pretty robust, especially compared to simple classification or regression tree approaches with respect to overfitting. And that's definitely an issue that can come up in just regular old meta-regression as well. And we almost always, even in this giant meta-analysis of 191 RCTs, we had more data than we could put in the model all at once, right? So we had to come up with this coarse set of decision rules of how we're going to advance moderators from earlier rounds into a final model. So you have to come up with these decision rules to avoid issues of overfitting and then basically just explaining the data you have at hand, which isn't really much of an extrinsic value. It's a non-parametric technique. So it's not anchored in assumptions of normality. And it's, like I said, it can be especially useful for capturing or highlighting some nonlinear and other complex interactions. The other nice thing about random forests is that by using that iterative sampling approach that's embedded within it, you can start to get a sense of some diagnostic information about the moderators that are in the candidate pool. Which ones are tending to show up as useful for making some decisions about splits and classifying the effect sizes and the studies into these different groups. And when you do this multiple times, you can maybe see some patterns and hopefully winnow the set. And I'll talk through how we did that in our application anyways. Okay, so what do we do? So step 1 is identify some initial set of candidate moderators. We already have this, right? So we had 43 kind of MUTOS aligned moderators that we had already planned for and used in our initial meta regression. So that's kind of our initial pool. It's 43 moderators. Then we need to figure out among the 43 moderators which were most important. Okay, so we needed to kind of winnow that down. We knew they weren't all going to be useful, and just having them all in the mix wasn't going to be especially productive. So let's see if we can winnow that down into some smaller set of most important moderators. Okay, so and this is where the random forest part really starts. So using the initial data, we conducted 20,000 clustered bootstraps. So we were sampling by study. So if a study had more than one effect size associated with it, we'd sample that study and all of its effect sizes all at once. So we do that 20,000 resamples of the original data. And each one of those instances is going to try to build its own regression tree and predict effect sizes. Okay, and then how do we determine variable importance in this process? Well, again, after this is being done 20,000 times, we can start to take a look at which moderators are showing up pretty typically and which ones aren't. The way that the random forest framework thinks about variable importance is that once a moderator is accepted into a regression tree, its observed values are used for predictions, but then it goes back in and it'll scramble those values. So it basically nullifies that variable. It's just kind of random noise in the model. And so a variable's importance is then kind of operationalized as the difference between the model's predictive value with that that variables, that moderators, real data in it versus its scrambled data, which is useful because that's the same operational definition used to judge all of the moderators' importance. So you can make some relative judgments about which ones are contributing more or less to predictive value. And so the basic question being asked there is kind of on average, how much does the model's predictive strength improve with the real moderator compared to a null version of that moderator? And because there can be some variation in that, even over 20,000 bootstrap samples, we repeated that process 100 times. So we had 100 replications of that, and each of those 100 replications within it had 20,000 bootstrap samples. So this is a computationally intensive process, which David managed beautifully. Okay, so I think, oh, and then our definition for kind of a cutoff on how important a variable needs to be. So across those 100 replications, a moderator needs to show up with a positive variable importance value, meaning that if it's removed from the model, that the predictive strength of the model tanks, like it goes down. So positive variable importance values, and they show up in that way at least half of the replication. So at least 50 out of the 100 replications, the moderators that are going to advance to the next round have that positive variable importance more times than not. And this is what we found. This is some output that you can get right out of the metaphors package in R. And you'll see here kind of a ranked variable importance. And the most important variable that we had was outcome type. And we actually forced our model, because we had pretty strong priors about this outcome type, given the results that we saw in our initial meta-regression model. So we forced our model to always split on outcome type. This is, again, like researcher developed versus standardized measures. So that was always included, and that was kind of by far the most important moderator among all of the candidates, even the ones that advanced to the next round. So we went from 43 down to these 13 moderators. So then using those 13 moderators, we kind of go back into the random forest framework, and we do fine tuning. And this is where we start to tinker with some of the parameters that can inform how splits are made and how stopping criteria are applied along the way. And so there are a few different tuning parameters that we can consider. The first is the type of meta-analytic weights that are used. And a side note about this, within this random forest framework, the meta-analytic weights are primarily used for selection, right? So in generating those bootstrap samples, studies with larger weights are going to be selected with a greater probability than studies smaller weights. And you can use fixed effects, fixed effects weights, random effects weights, uniform weights. And so we tried all of them out. Again, we're not in this exercise for any strict inferences. We're exploring and trying to interrogate the explanatory value of our planned meta-regression model. So getting the weights perfect isn't really central to this exercise. We're trying to figure out if we can get the data and this machine learning algorithm to optimize predictions and figure out the distance between those predictions and our planned model. The other tuning parameters that we can tinker with are the number of candidate variables to draw from at each split. So this is kind of that within study sampling technique that I was referring to earlier, within sample sampling technique. So at each point in a split, the random forest algorithm can choose from any of the available candidate moderators that haven't been used for a split already, And the way that we set it up is to draw a small sample of only 3 of the available moderators in each split. And what that does is that limits like that prevents a model from always choosing the most predictive, right? So if we hadn't forced the model to always split on outcome type, we would run the risk of that just being chosen anytime it was a candidate. So this forces the random forest algorithm to choose among less desirable combinations of moderators along the way. So you have these things that can then move up in the decision tree or move down in the decision tree. And hopefully that mixing and matching via moderator sampling allows for us to pick up on some potential nuance and how these interactions and relationships may play out. So that's the idea. And then the final tuning parameter that we could tinker with is the number of studies or number of cases required in the final classifications or the terminal nodes, and we tinkered with that as well. And all of the specifics on this are included in our paper, which I'll give a link to, and the supplemental materials associated with that. Okay, so the next thing that we need to do is cross-validate the predictions from the random forest model. And so to do this, we used leave one out. Let me take a step back. Why cross-validate? This is, again, trying to figure out if there's some extrinsic value in the explanatory strength of the model that you're putting together. So if you're just using the model to explain all of the data you have in hand to explain all of the data you have in hand, it's not clear that that's got some relevance to the future or some other study or whatever it is. So we use this kind of leave one out cross-validation approach, looping over all of the 191 studies, basically conducting 191 different random forest models, predicting each study's effect sizes based on the data from the other 190. And so we did that for each of the models, and we ended up with these cross-validated predictions. And these cross-validated predictions function as really kind of like a super moderator. And you can think about them as like a composite variable that has all of the conditioning that came out of that random forest model that you could then plug into a typical meta-regression framework and then do your bake-off where you compare against the MUTOS meta-regression framework. But to make that a fair bake-off, a fair comparison, we also wanted to cross-validate the MUTOS model in the same way. So we did that because we hadn't done that originally. We just ran our meta-regression model and looked at the results. And so we cross-validated the MUTOS meta-regression model in the same way, generated those predictions, and now we have 2 sets of kind of predicted effect sizes, which are kind of our super moderator covariates, and we want to see how well those explain variation in the observed effect sizes. So what did we see? If you remember earlier, a few slides ago, where I had the sad trombone with 10% of our heterogeneity explained by our planned meta-regression model, it got a little bit worse after we applied cross-validation. So we're now down to 8% of heterogeneity explained by our best intentions, our best thoughts in our MUTOS meta-regression model. The random forest model ended up explaining about 13%. So it's not like it's apples and oranges here, or that there's something especially revelatory clearly happening in the random forest model that we weren't picking up. But it's large enough of a difference that we wanted to figure out, okay, well, what actually is going on here? And we'll go through some of those comparisons. So here's a quick summary of kind of what each of the models were using as priority moderators. So in both of the modeling approaches, researcher-generated versus standardized measures were priorities. That was unequivocal. They both thought that a distinction between technology delivered versus other delivery vehicles of interventions was an important feature to keep around. The MUTOS model did not advance average student grade level into the final mixed effects analysis, but the random forest consistently found that to be an important moderator to consider. So it was kept around in the random forest framework. Same with intervention length, number of weeks. We didn't advance it to the final model under the MUTOS meta-regression, but random forest thought it was pretty important. And then we saw a bit of a flip where we had advanced supplemental time versus other intervention types, as well as publication year, but the random forest decided over those 100 replications that they weren't especially helpful for optimizing predictions. All right, so here's a graphical comparison of what we're seeing across a few of these continuous moderators that we had in hand. So remember, the random forest meta-regression model picked up average grade as an important moderator, but we didn't advance it into our final model in our planned meta-regression. So this is just a summary of the relationship between average grade level and the average predicted effect size at each of these average grade level values here. From our MUTOS meta-regression model, right? These are going to be linear relationships. The p-value that we had associated with this covariate in the initial round of analyses was 0.13, so it didn't advance, right? It needed to be 0.10 or smaller. But in the random forest model, so when we kind of average those predictions from the random forest model that are informed by all of those possible permutations across those 20,000 samples, we see a little bit more of a nuanced relationship between average grade level and average predicted effect sizes. It's still kind of trending negative from kind of the early grades to the higher grades. But there's a bit of a jump in responsiveness in those early elementary average grade values that definitely was not showing up in the MUTOS meta-regression that we had initially planned. Same thing with intervention length. So this is just kind of like the number of weeks that an intervention was implemented for. In our planned meta-regression, in that first round, within the treatment bucket of MUTOS, we saw a pretty flat relationship between intervention length and average predicted effect size. And it was definitely not significant. But when we go into the random forest predictions and look at those averages across the same values, it's quite a bit more nuanced. And there seems to be some bit of a jump in responsiveness for interventions that are implemented for around half of an academic year. Same general kind of slight negative trend across the whole space of the moderator, but definitely not something that we're picking up in our planned regression model. Okay, so now I'll get to some of my thoughts on strategies and considerations, and hopefully this leads into more of a discussion. So I'm still, this was a really fun exercise for all of us. We learned some new techniques. We got to add in kind of a new set of analyses that I think really helped flesh out the veracity of our best thoughts from the get-go, or the utility of those thoughts from the get-go. But I don't think, I'm still not quite there to jump on board saying like we should just full bore machine learning all of our meta-regression applications. So as much as we possibly can, I think it's good to still start with kind of a theoretically grounded set of moderators and a plan for how you're going to put those together, even if it's not perfect. Try to come up with a plan for how you'll get those into an analysis that's going to be substantively useful to consumers, especially practitioners. But I would say that, meta-regression, even in this large this fairly large meta-regression that we did, it's still a pretty small sample technique. And so I think people doing systematic reviews and meta-analyses are just, they're gonna commonly run into this problem of, how do I choose from all of this data I just spent a year, 2 years coding, and put it into a model that has some meaning to it. So we're going to continue to struggle with, even with our best theories in hand, the data may overwhelm the ability the number of moderators, and they're relative to the number of data points may still overwhelm. So I think, I also think that data-driven approaches like random forest models can help us better understand that relative explanatory value of our best theory-driven approaches. This seems like more of a no-brainer to me, that this should be more of a companion set of analytical techniques that people doing systematic reviews and meta-analyses should just have in their pocket, a tool to call on and think through. And if nothing else, planning something like this will hopefully also get you to think more critically about how you want to put those moderators together in the first place, which is something I don't think we do well enough. And data-driven approaches come with their own sets of critiques, right? So, and those shouldn't be ignored, right? So you don't have to look any further than all of the historical debates that have happened between exploratory factor analysis and confirmatory factor analysis, and people yelling at each other for using data-driven approaches versus theory-driven approaches. But I think the bar is pretty low right now for applied meta-regression. We're not doing a whole lot of complex model building right now. We're not doing a whole lot of thoughtful model building right now. So I think there's ample space to start to incorporate some of these machine learning type methods to help us refine our theories and our hypotheses, and help us capitalize on some potential lost opportunities in our analyses and spur some additional thinking, even if we aren't going to run with those as just clear confirmatory results of what's happening in the universe. I also think, this is a super active area of research and development in the research synthesis method space. And I think there's going to be a lot of new tools. The tools that are out there, the meta-forest package, the meta-cart package, others, they're accessible. And I think, in 5 years from now, there will be a new wave of techniques or add-ons to existing techniques that may even make us look back and wonder what we were thinking and doing what we did here in this application. And that's it. That's all I have. I'm hoping we can discuss. I'm including some resources here, and I'm happy to share these slides out to James and Mega and Terry to post or whatever we do. All of our code, our data are registered on OSF. We have a Shiny app that uses all of the data that we use in our analysis to do some exploratory and kind of build your own meta-analytic exercises. A link to our papers there, and then some really good Van-Lisa writing on meta-forest and applications and small sample meta-analysis. Really good and accessible papers to think through and read through if you haven't done so already. They were super helpful to me, anyways. So that's it. So I'll stop sharing and take questions. I haven't been closely monitoring the chat.
There's a comment by Carol saying it'd be great for you to give this talk at our method speaker series at UBC.
Okay, well, yeah, thank you for the invitation, Carol.
I gave Carol your email address. Sorry, Ryan.
No problem.
And we've got a good amount of time for questions. Feel free to drop them in the chat or use the hand raise feature on Zoom if you want to ask a question verbally.
There's a question from Reza. How do you think the modeling strategy might depend on the audience of the meta-analysis? For instance, do you think those who are merely researchers and perhaps have read or done some primary studies might prefer to see some sort of one-on-one correspondence between meta-analytic findings and primary studies.
Oh, interesting. Well, I don't know how much the modeling strategy within meta-analysis should depend on that, right? So at least the goal for us, like we were doing a meta-analysis for heterogeneity, and going into it with a strong belief, strong prior that we're going to see a wide distribution of effect sizes, and we wanted to plan a model that was maximally predictive. And then we wanted to see if we could find an even better model than that. So that was kind of the goal. In terms of correspondence with primary study results, this was in some ways tapping into a secondary goal of mine. One of my biggest pet peeves that I have in evaluation work, especially, is that in a one-off evaluation, folks walk away with a null finding or something that's not super impressive and just immediately overgeneralize that finding that nothing works. Nothing's working here. We found absolutely the opposite. If you looked at the 95% prediction intervals from our meta-analysis, and you can actually back out some useful probability statements, like what's the probability of randomly identifying an intervention that has a positive impact, and that estimate was close to 70 or 80%, which is a far cry from nothing works. So I think we shouldn't expect that meta-analytic findings and individual primary study results to always correspond. The goal of the meta-analysis is to put together all of those disparate pieces of information to make sense of how well we're doing kind of at a population level.
Next question from Selchuk. Is there any suggested ratio between the number of effect sizes and the number of moderators, or what would be too many?
Oh, there are definitely a bunch of suggested ratios in the literature. I mean, you can look in just the regression literature itself for suggestions, 10 units per parameter, et cetera. And this is something that we quickly gets out of hand in a meta-analytic framework, right? So that's one of the helpful, I see as one of the potentially helpful aspects of random forest methods, machine learning methods generally, to help make some of those decisions and identify among things that we think should be related to effect sizes, which ones are. And you can do that simultaneously with setting some rules about how much data you need to have populating each of those classifications. So it's not a strict rule, but I mean, keep in mind, if you're doing meta-regression, you're doing small sample regression, and you need to be cautious.
Next question from Philippe. Meta-regression using GAM's model, GAM, generalized additive models that include semi-parametric approaches. How difficult is the barrier that we can expect in the reviewer's process for these new methods?
I don't know.
That was two questions in one. I mean, the first one is just if you are familiar with the GAM models, if you are seeing this kind of models in meta-regression, that will be the first question. That's it.
Okay, yeah, I have not applied those, and I haven't seen them a whole lot myself, and I haven't worked with them, but I don't know if there are others on here who have put them to use more frequently. I know of a few applications that have existed. I think Will Shadish had a student in the not too distant past who was using some of those approaches. And I don't know, Terry, James, others, how receptive are reviewers to them? In applied journals, technical, if you're going to spit out a paper that's highly technical and reads more like a methods paper, I think you will run into barriers. So it's a matter of I think managing transparency in that process and trying to keep the essential pieces in the main narrative without adding too much weight to the paper with unnecessary methodological information. So we put a bunch of stuff into a supplement, for example. Basically everything I went through today was in a supplement. We had some high level kind of narrative overview of everything I talked about here, but almost all of it was in a supplement. But yeah, Terry, I don't know. What are your thoughts on reviewer barriers?
I'll let James go first. Looks like James has.
Oh, no, I was just
thoughts,
going to
yeah.
comment on the technical aspect of it.
Yeah.
I don't think there's been a lot of work on GAMs in the meta-analysis context, but that might be partly because I guess I think of GAMs as particularly useful for modeling like flexible shapes in a continuous predictor, and meta-analysis tends to have a lot of categorical predictors. There's not in Ryan's example here, I think maybe you have one or two that you would conceptualize as continuous. So that might be why there's more emphasis on these regression or these regression tree based techniques.
As for reviewers, I feel you. It's hard, and it varies by journal and so forth. So I'm sorry. Hopefully, some editors are better than others. That's all I can say.
Next question by Jay. I've tried following along with Ben Lisa's metaphors tutorial in the past, but found it difficult to understand how to apply. Could you talk through your team's decision-making process for applying parts of Van Lisa's paper to your meta-analysis?
Oh gosh, is David on? Did David make it? I mean, David's the one who first navigated that paper. There are a few different resources. So Jay, one of the links I pasted was a book chapter. Do you have that one? So the Van Lisa, I think it's the Van Lisa 2020 citation that let me see if I can.
Yeah, I think we can get that. Yeah,
Yeah,
we might also just talk to David.
Yeah. Yes, David will definitely be happy to have a discussion on how we set this up. But David shared that chapter with me, which I think is a really it's a fairly unintimidating intro to this world of random forests and regression trees and some of the strengths and limitations. Really well written, I think. Highly recommend it if you haven't already done it.
Okay. Next question from Peng. Is it possible that by coding more moderators from the database and run with machine learning can help explain more heterogeneity? If yes, any thoughts how to identify those moderators besides using theory?
Yeah, this gets into like I see a kind of a natural tension that may start to crop up as these types of methods become a little bit more prevalent. Is let's just code everything we possibly can on every given study and then let the machines come up with a model, which is an approach. But I also think, I think there's some lessons learned about kind of gauging expectations on what the explanatory value of even your best coded, best implemented meta-regression analysis is going to tell you at the end of the day. We can only get down to a certain level of granularity relying on study reports. I think there's so much more that's happening under that surface that we just we're not able to tap into on a regular basis in typical kind of aggregate data meta-analysis. I think there are some opportunities in individual participant or individual patient data meta-analytic techniques that might be able to start to make use of different construct different moderators from lower levels that we wouldn't typically have access to by just relying on reported information. I think that's just a natural limitation of aggregate data meta-analysis. Level of reporting and transparency and access to the generating data is gonna, I think it's gonna be a consistent cap on what stories we can tell with our best intention meta-regression analyses.
Okay, next question by Carol. Do you test collinearity of the variables in meta-regression first before entering them in the model? If yes, how do you decide which to exclude if two or more are correlated?
So in typical meta-regression, yeah, that's something you can do. I haven't done it a whole lot. Again, I kind of mostly let in what we did in this application, kind of the model building steps from MUTOS into the final mixed model. We didn't winnow any moderators based on some correlation with other moderators. But it's a step that one could apply. And it's something that actually is, I think, a helpful advantage in the random forest framework for managing, because again, when you're kind of sampling among candidate moderators, you may sample, one of these highly correlated models in one instance and split a tree earlier on or split a branch earlier on, and then do it later on in a different permutation, and just over those many different bootstrap samples that they kind of cancel each other out eventually. So it becomes, I think, less of a big issue in the random forest framework than it does in typical kind of regression building frameworks, if that makes sense.
You have 1 minute, I think, left, not even. Next question by Karen. Any thoughts on how much of the heterogeneity is explained by measurement error versus explained by moderators?
Oh, well, like explained by measurement error? Ooh, I mean, hopefully not a whole lot, but I do believe that the relatively low proportion of heterogeneity explained is absolutely in part due to measurement error in the coding process, right? We have to come up with decision rules about how to classify certain features of even sample members. Like, what do we do when we have means and medians and ranges reported across different, there's all sorts of measurement error that creeps into our coding processes. So I absolutely think that that's a limitation. I don't think that it's measurement error or just random noise that we're seeing as kind of explaining the heterogeneity that we captured here. And that's something that I think the random forest approach is helpful to kind of interrogate a little bit.
Ryan, I think Karen might be talking about like the measurement error in the primary study results.
Oh,
right, like differential reliability of the outcome assessments.
Oh, I don't know. I'd have to think some more about that. For most of the, we didn't have a whole lot of reliability data that we were able to code from. It's often not reported, so I don't know. But I do know, at least with those standardized measures, those are pretty darn reliable. And many of the researcher developed measures that were entered into the mix, where we could observe reliability estimates, they tended to be pretty high from what I recall. But that's kind of anecdotal.
I think we're right at our time limit here. So I will, I guess I'll call our question and answer period to a close. Ryan, thanks so much for presenting this work today. I think, given the number of people still hanging around here and the range of questions that we've got still coming in, it's an indication that this is really promising and important direction for meta-analysis work in the future. So thanks very much for sharing it with us.
Yeah, thanks for having me. This was fun.
Our next seminar will be coming up in a month. We'll have Dr. Mariola Moyeret speaking on meta-analysis of single case research designs. So please do join us for that. Keep an eye out for announcements about that coming up.
Sounds good.